Okay, in the previous class, we talked about the frictional head loss, the major losses, okay, of the piping system. Now, today, let's talk about the minor losses, okay. In the piping system, you will have some other losses other than the friction. You have the different components, like bands, elbows, the flow meter, okay, pressure gauge, valves, everything contributed to a little bit of loss to the whole piping system. Okay, so since there are so many different components, so we cannot theoretically model each individual of them. So what we do is we use a K as a minor loss coefficient. Okay, we can experimentally determine this coefficient. So the minor loss expression will be look like this. Similar to the frictional head loss, all those losses are related to the velocity of the flow, right? So we still keep the v squared over 2g terms. So minor loss equals k, a coefficient, minor loss coefficient, times v squared over 2g. Okay, so now the entire loss will be equals to the frictional head loss plus the all minor losses. Okay, so now we need a k, right, for each component, for each minor loss. Okay, k is the minor loss coefficient. So in the textbook, table 10.3 on page 381 shows the case for different components. Okay, so let's look at the textbook. Okay, so this is the table 10.5, the loss coefficient for various transitions and fittings. Okay, so different component, different transition or fittings, you have a different case. Okay, see for this is the table. So for example, the first one is a pipe entrance, they call it pipe entrance. Okay, so look at that. Okay, pipe entrance, so it depends on, see the different k values, right? And it depends on the r over d. What is r and the d? Okay, d is the pipe diameter, right? R is the radius of the curvature at the entrance. Okay, so depend on the different r over d. If r over d is 0, what does that mean? That means it's a sharp entrance, right? There's no curvature. Okay, the k will be the biggest, 0.5. Okay, then the greater the r is, that means more gradual, curvature, more gradual entrance. Okay, the lower the k will be. When r over d greater than 0.2, and the k will be 0.03, very small, almost negligible. So that tells you if you design a piping system at the entrance, you want to make a curvature like this, gradually get flow into the pipe, let the flow. Okay, so that's example. What else? Let's see. This is a contraction. Okay, if you have a contraction, your k value depending on the diameter ratio between out and in, d2 over d1. d2 is the smaller pipe, right? d1 is the larger one. d2 is after the transition, d1 is before the transition. Okay, depending on the ratio, diameter ratio, and also depend on this theta angle. Look at this, that's a theta transition angle. Okay, you will have different k values. Okay, same thing for the expansion. Okay, be careful. In expansion is d1 over d2. d1 is the smaller pipe. Always in the numerator is the smaller pipe. Always the ratio is small pipe divided by larger pipe. Okay, so depend on the d1 over d2. Depend on also the theta angle for the transition. You will have a different case. I want to note here what means d1 over d2 equals 0. The first item, first data. Okay, d1 over d2 0 means d1 is infinitely small comparing to d2, which is a situation as a outlet, pipe outlet to a reservoir. Okay, the reservoir diameter is treated as infinitely large. So D1 over infinitely large will be 0. So that first K, when D1 over D2 equal to 0, K equals 1, that means a outlet, exit of the pipe to a reservoir. Okay, notice in that situation, if D2 is infinitely large, then theta is 180 degree. Okay, theta 180, so K is 1. So that's a special case for the expansion, is the exit of the pipe. Okay, there are some other case like a band, 90-degree meter band, and 90-degree smooth band, without vein, with vein. So they have all kinds of case. Okay, you have to learn how to read this table. With the band, the smooth band, they also depend on the R over D, right? R is the radius of the curvature of the band. Okay. With vein is K equals 0.2. Without vein, I think is depend on R over D, right? For the band. And it listed all the case for the valves. Okay, all kinds of valves: globe valve, angle valve, gate valves, open and half open. Okay, elbows, teeth, all components. There's a K associated with it. So if you have a component there, it will be a little loss to your piping system. Okay, so this is the table 10.5 in the textbook. You need to learn how to use this table as well as the Moody diagram. Now let's come back to our notes. Now you know how to model the minor losses. So the combined head loss of the pipe system will be, I write down like this: HL equal to summation of the frictional head loss if you have a multiple pipe in your system. Okay, that's why I put the summation. Plus summation of the minor losses. Yeah, you have many different fittings, fittings, and the transitions and components. Okay, each one will have a K. Okay, so now you know how to calculate the total loss of a piping system. Okay, so it's the frictional loss plus the minor losses. Okay. So there, the example 10.7 in the textbook, page 383. Please read it. It's a very simple problem. It's just tedious, have different components. Just add all the losses together. Okay, that's the total head loss. Okay, there are some other theories and problems in this chapter. Okay. There's some other materials, okay? Let's quickly go through the rest of the stuff. First one is the non-round conduit, okay? Non-round conduit. So not very often you will see non-circular pipes. Not very often, okay? Most of the time the piping system will use circular pipe. If you have a non-circular pipe, okay, we don't have any new models for non-circular pipe. Instead, we just use something called hydraulic diameter. Okay, so all the equations are the same, okay, but the diameter part, we use hydraulic diameter instead of the real diameter. For the non-circular pipe, you don't have a diameter, right? But you can calculate a hydraulic diameter, a representative diameter of that shape, of that cross-section. Okay, the hydraulic diameter equals 4 times cross-sectional area divided by the wetted parameter. Okay, so if you look at this, if the shape is a circle, then the hydraulic diameter will be identical to the diameter of the circle. Okay, if you put 4 times cross-section area, quarter pi d squared, 4 and 4 canceled. Pi d squared divided by the related parameter is pi d. So hydraulic diameter will be equals to just diameter for the circle. But for the non-circular shape, you can calculate a hydraulic diameter. Okay, so then use that representative diameter to do all the calculation for the losses. Okay, but there's no new equation for non-circular conduits. Okay, equation are all same. Darcy-Weisbach equation like this. Okay, and the minor losses equation. Okay, for the losses. Okay, but instead of using D for the circle, use hydraulic diameter for the non-circle. That's it. That's all you need to remember. Okay, I think there's also example 10.8 in the textbook, page 385. Okay, so you will see it. Take a look, and it was very simple. It's just calculate hydraulic diameter. Okay, then that's it. So the next item topic is the pump in the piping system. Okay, so we mentioned many times the pipe, right? The pump, right? In the energy equation, the pipe, you will have a pump head turns, right? Look at that equation. So for example, there's a situation like this. You have a lower reservoir, okay? You have a higher reservoir. The purpose of the pump is to deliver fluid from lower place to high place, right? That's one of the purposes for the pump. There are two purposes, right? The other purpose is to create the flow, right? Pump is to create the flow as well as to deliver the fluid from lower places to high places. Okay, this is a typical example. So for this example, section 1 and section 2, both surfaces, you can write down the energy equation, right? Okay, you have a HP, you have a losses. Okay, so velocity 1 to then can be canceled, the pressure 1 to 0. So the equation becomes this: pump head equals the elevation differences plus V squared over 2G, and the losses, right? The combined losses. Okay, so that equation tells the story. Your pump head required, the pump head required by the system is to overcome the first term, which is the elevation difference. Right? You try to overcome the elevation difference, as well as to overcome the losses. Right? Okay. So pump head is to overcome these two items, to overcome the elevation difference as well as the losses. So based on this equation, you can write a curve here. Okay, there are two curves in there. Okay, this is called the system curve. This is what the system requires. This system doesn't care about what kind of pump you placed in there, right? That's the system equation. So the system requires that much pump head. Okay, so that's the system curve, going upward curve. Okay, that's the system curve. See, that's going up with the flow rate, right? Velocity, flow rate is in the x-axis. Pump head is in the y-axis. So when the velocity increases, look at this equation. When velocity increases, your pump head need to increase. That's why the curve is going upward. Okay, the initial value in the y-axis is z2 minus z1. When velocity equal to 0, your pump head is z2 minus z1. So that's initial value on the y-axis here. Okay, this is system curve. I also placed another curve in this for comparison. That's called pump curve. Okay, look at the going downward curve. If you buy any pump, the manufacturer will give you a pump curve. That's a characteristic of the pump. It's like any mechanical device. Okay, it's always shaped like this. It's going downward. When flow rate increases, the pump head can be produced by the pump will decrease. Okay, like all the mechanical devices like this, just like a car. If you drive faster, you have to you can tow less, right? If you want to tow a boat, you better drive in the low gear and drive slow, okay? So this is the characteristic of the pump, okay? If you want to, for that same pump, if you want to deliver faster flow, you have to sacrifice the pump head, right? If you want to deliver a higher pump head, then you better run it at a lower speed. So that's the same thing as like a car. Okay, but if you place these two curves together, there's a intersection. We call it the operating point. Okay, operating point. The meaning of the operating point is if you place this particular pump in this particular system, it will operate at this operating point, which means this particular flow rate and this particular pump head. Okay, that's very useful in the pump selection process. So you have, if you identify your system curve, if you find the manufacturer pump curve, if you put together, you will know, okay, if I place this pump in my system, how much flow rate it will produce and how much pump head it can produce. Okay, so that's the meaning of the operating points. Okay, this is the pump topic. Okay, there's also example 10.9 in the textbook. I will give you some homework problem also to use this pump curve and the system curve to solve problem. Okay, but there's no new knowledge here. The system equation is just basically is chapter 7's energy equation. Use this equation, you can find the required pump power, pump head for the system. Okay. The last topic I want to mention here is pipe in parallel. Well, often you will see a parallel piping system like this. Okay, this is a piping inlet pipe. You bifurcated into two branches, A and B, right? Then go back to the outlet, right? So for the system like this, the question you will always ask, hey, the route A and route B, they may be different pipes, different diameter, different lengths. So which one will give more losses to the system, right? That's always a question. But interestingly, you will think if A is longer, much longer than B, it might give you the greater losses, right? Vice versa. But let's see if that's true or not. Okay, so I put 2.1 and 2. You can write down the energy equation between 1 and 2, right? From both routes, right? So route A, you will have an equation, right? Okay. Route B, you will have an energy equation between 1 and 2, right? Okay. So route A, you see, look at the equation: P1 over gamma Z1 V1 square over 2G. And at 2 is P2 over gamma Z2 V square over 2G plus a loss HLA, let's say loss of the branch A. But for the B route, you look at the equation. There's a loss of B, right? HLB. Look at these two equations. Okay? What this equation will tell you? Everything else are the same. Okay, if this equation, the two equation has to need to stand, then HLA has to be equal to HLB. No other possibilities. Wow, that tells the story. No matter how long the A is, or how short the B is, or how large the A is, or how small the B is, whatever the configuration of the two branches. Okay, it tells you, as long as they're in the parallel piping system, the losses has to be the same. Okay, HLA has to be equal to HLB. So if you extend it right out, the HLA and HLB, frictional head loss will be FALA over DA equal to VA square over 2G equals to FB LB over DB VB square over 2G. Okay, now this equation tells the story because the loss has to be the same. Everything else are different then, okay? let's say if LA is much longer than LB, let's say diameter are the same, okay, DA, DB the same. FA and FB, you know, it might be different, but not that different, right? The variation in friction factor is a little bit small. Let's consider they are almost the same, identical. So LA, if LA is greater than LB, DA is the same as DB, FA is the same as FB. What about VA and the VB? Because of this equation, loss has to be the same. If LA is greater than LB, your VA has to be smaller than VB, based on this equation. That makes sense, right? If your pipe is much longer, if your route, the branch is much longer, you have to sacrifice the speed. The speed in the pipe has to be smaller. Okay, vice versa. Let's say if LA is the same as LB, the lengths of the two branches are the same, but DA is much greater than DB. If DA is greater than DB, what happened to the velocities in the two branches? If DA is much greater than DB, then VA has to be greater than VB, right? Velocity has to be bigger on the larger diameter pipe. Okay, that makes sense. If you have a piping parallel system, the larger diameter branch will capture larger flow, larger velocity, right? The longer branch will capture less flow and less velocity, right? So the larger pipe and the shorter pipe always have the advantage on capturing the flow based on this principle, piping parallel. Okay, again, the losses in all the branches are the same. Okay, and because of the loss are the same, because of that, your velocity, the flow will be different. Okay, it's not like the loss are different. It's not like that. Okay, very important. This is in the piping parallel. So these are the small topics for the chapter 10. Other than the major hair loss, friction hair loss is the important part, right? These are also the topics in chapter 10. So I will assign homework problem for all of them.